So I welcome you all on the third day of the workshop. And we have Professor Janani Sri Muralidharan with us. She's going to start the session. And today is 21st February, and we observe International Mother Language Day today. So a very happy Mother Language Day to all of you. So let us begin with the session now. First, we'll have a theory session by Professor Janani on natural congestion and conduction. And then we'll move forward to have an hands-on session by Mr. John Pinto on the same topic, on the related topic, which is Laplacian form, natural convection in cavity. Okay, so over to you, ma'am. You can start the session.
Good morning, everyone. I hope you've had a good first 2 days. And I understand that you've done meshing basics as well as flow. Okay. So today we're going to deal with, we're going to start with heat transfer. And this session, we would like it to be a little bit more, non-conventional, meaning it will not be a full lecture-ish and then you will not go to a tutorial session. We kind of break it up. And today's sessions are going to be about, conduction and convection. So typically, when you talk about heat transfer mechanisms, you have 3 modes of heat transfer. We all know that: conduction, convection, and radiation, right? So since today is a very flow-based workshop, we're not going to be dealing with radiation. We'll only be dealing with conduction and convection. And since a lot of activities industrially is in forced convection, I think there's a separate session for forced convection. Today's session, we're going to talk about the other 2 forms, which is conduction and natural convection. Okay, so which is not, bulk motion velocity driven. It's going to be, density driven based flows, which is natural convection. So in today's lecture, the way we're going to do about it is we're going to do conduction and some hands-on session with conduction. Then we'll come back and I'll kind of talk to you about natural convection and a related problem. So it's going to be divided into 2 parts. Now, as far as conduction is concerned, I'm just, how many of you are, reasonably okay with conduction? It's some of the basic things. So I don't think it's necessary to kind of talk about it, except to kind of probably give you a refresher of what I showed you in my first day class. So can you all type whether conduction is a familiar topic for you? I absolutely presume it should be. Yeah. So I see a lot of yeses. So I don't think I have to kind of talk about too much about it. But I'm going to talk to you in relation to what you're going to be doing today. Okay. So what we're going to be looking at today is, so this is going to be a simple rod. Okay. And we're going to look at conduction through this. So what today John is going to show you is a solver called Laplacian form. Okay, so the main idea is we're not taking a full-fledged heat transfer solver, but for starters, just the Laplacian form we're going to be taking. So the Laplacian form, what do you think the equation will be? Basis the name. Can you make a judgment? Why do you think we've chosen Laplacian form for conduction? Yeah, good, Shiva. So essentially, conduction is a diffusion-based equation, correct? So this is something that you see over here where there is a diffusion term, okay, and a source term added to it. So diffusion in itself means Laplacian. So the solver is purely a diffusion-driven solver. And we're going to show you how using this new solver, you can model simple conduction problems, okay? So what is the purview of conduction problems that you will be doing? You would initially have a source term. Okay, and we're going to look at how the temperature profile changes because of this source term. And I think we're going to have you do an exercise where there is a temperature difference and how does this solver provide results and does it match with the analytical solution. So that's what you're going to be learning about. Okay. Now, while you're setting up the problem, the one that John is asking you to do, we will recap certain important points about the intricacies involved, which I want you to pay attention to, and maybe if you have the time, can fiddle around with it. So taking the Laplacian equation, what we do is we integrate every cell. So if P is the cell, we're going to integrate it from the west to the east, right? So when we are integrating, we have this gradient term that is formed plus the source term plus delta x, correct? Now, when we move on to choosing this gradients, it is TE minus TP by the distance between the cell centers. Okay, so this is a particular numerical scheme. Okay, anyone want to venture what that scheme is? Okay, that's okay. I mean, yeah, largely a central difference kind of an approach, wherein you say that it's going to be a linear variation. In conduction, you know that is more or less okay, right? So I want you to, while you're running the solver, probably look at the FE schemes folder, right? And I want you to kind of, at that point, look at what is the scheme that is being used there. Okay, and then we will kind of briefly discuss what it means. Okay, so with this background, that you're going to be doing a conduction equation solution using Laplacian solver, I would like to get into the work of actually setting it up. So I would like to now go ahead to natural convection part. Okay. I think everyone is aware what natural convection means, that it is a flow, a bulk flow driven predominantly due to some kind of a temperature difference, which results in some minor density changes. Okay. Now, apart from the physics, the challenge comes when you have to model your boundary conditions and the equations to solve natural convection. So one needs to understand first why there is a challenge involved. So before doing this, let me just go back to my previous presentation, which might be important here. So it becomes important for us to first understand how a normal Navier-Stokes equation is solved, right? So in your Navier-Stokes equation, you are going to have a matrix wherein there is, what are the equations you're solving? There is the momentum equation, right? And then the, I think the previous page is, yeah. So you have the momentum equation, but you have the continuity equation as well, correct? So in a pure flow problem, what are the unknowns that are there? That is the U, V, W, and then the pressure, correct? So when you have the U, V, W, and pressure, you need to have 4 equations to be able to solve it. Okay. You have 3 equations for the velocity, different components of the velocity. But for pressure, you don't have an exclusive equation. You just have the equation for velocity again, correct? So like I mentioned earlier on Monday, the simple algorithm tries to rework this, okay? So what it does is, initially it will not have an equation with the pressure term, but it will rewrite the continuity in terms of pressure, okay? So there will be one momentum equation, but there will be a continuity equation, but in terms of pressure. The terms there will be in terms of pressure. So then you will have 4 equations, 1 for pressure and 3 for velocity. So what they will first try and do is, you will have to assume initially there is an initial field. So you will assume, have the boundary conditions as an initial U that you will put in and calculate basis the equation and intermediate U for the next time step. Okay. So once you've got an intermediate U, you will calculate the mass flux from the U, correct? So when you calculate the mass flux, that mass flux will come into the continuity equation because you have to do the continuity, and that will give you the pressure. I'm talking in a very basic sense. There are intricacies. I don't want to go into it. So what are you basically trying to do in a only flow, not energy, not temperature? All you're trying to do is you're trying to iteratively solve basis a initial condition of U. You get a intermediate U value, which you will plug in into this and get a pressure value. Now, this might not be correct in the first round. So iteratively, you will go till the U and the pressure satisfy both these equations, okay, for the next time step. So this is how you do the simple algorithm. Okay. So now let me go back to the natural convection, right? So in natural convection, the challenge here is that there is no initial flow. All your boundary conditions do not have flow. And, a pressure difference is not there because you don't know the pressure difference, correct? Now, purely there is only a temperature driven basis condition where the density is changing. That is what is driving the flow. But we are solving a compressible equation becomes very tedious. Okay. So for natural convection, there is an intermediate assumption that is being made, which will help you work in the incompressible framework. Okay. So all of you are aware of this equation, set of equations, which is your, you have your continuity equation, correct? And then you have your momentum equation. So I'm going to try and do this for flow over a vertical plate. Okay, so if you see flow over a vertical plate that's here, you have a vertical plate that's heated of height h. Okay, I want you to pay close attention to the coordinate system here. This is my own choice, right? So normal to the vertical plate, it's x. And along the vertical plate, it is y. Now, because the vertical plate is going to be heated, there is going to be a boundary layer that is set up, right? There's going to be a density difference. So flow is going to start flowing up here. And after the heated plate, it will lose energy. So it will probably just circle around, lose the density difference, and probably drop down. So there is a convection current that is set up, right? So that will go like typically like this. And this is purely density driven, correct? So you are going to get a boundary layer of sorts where flow is flowing. Okay. You know that far upstream, U is equal to 0. There is no movement. So your velocity profile is going to vary from 0 at the wall to a peak middle of the boundary layer to again 0. Okay. So this is slightly different from your internal flows where, you don't get 0 at the core, right? Okay. So now for this, if I'm going to start writing the generic equations, I have the continuity equation. I have a momentum equation in the x direction, right? So I think I'm not going to go again over here. This is a pretty standard equation, okay? Now you have the y momentum equation. Okay, now if you look very carefully in the y momentum equation, there is a dp by dy, which is equivalent to a dp by dx, but there is also an additional source term I have added. What is the source term? The gravity-based source term. Because the density changes, which is driving the flow, you have a source term called rho g. Okay, so I've added a source term for the density. But because the flow is driven by a density change, which is driven by a temperature change, this rho here is a function of T, temperature. Okay. So this row alone, I'm going to keep it as a function of T, except the momentum and energy is interlinked with this particular term, which is density variation with time. So for every time step, you'll have to know the time, the temperature, and hence the density. Okay, so it's an interlinked equation. Okay, that's point number one. Point number two is, if you notice here, and the question in your mind will be, this density, is it also a function of temperature? So the answer is no. Okay. An approximation, which is called the Boussinesq approximation, you must have heard of the term, right? So Boussinesq approximation basically says that in large parts of the domain, okay, the main momentum equation, I presume it to have constant density, okay? The only real driver of the force, which is the source term, is driven by density difference. So I am going to, within a small range, the flow is not going to be, near Mach number, right? So I am just going to presume that density for all other transport purposes, like advective and diffusive, can presume constant density. But the driven flow by the source is the temperature difference. So only that term will be temperature dependent. Okay. So this is called the Boussinesq approximation, which is a very important approximation here. Okay. So now you are familiar with the equations that we are using. But can we, for the vertical plate, simplify it further? Okay. So what you see here as the following, right? So I will draw the domain again. And you have the y direction and the x direction, correct? So the first approximation I say is u in the y direction, okay? The gradient of u, the Laplacian of u is negligible, very negligible, correct? Because your flow is happening here, agreed. But is there a change in the velocity profile as you move up? Not significant, not in the y direction. Have an analogy to your pipe flow, right? So your gradient at the wall with respect to your normal to the wall is more than the axial. So you remove this term, you neglect this term. You also say that convection driven dou p by dou x, right, in the normal direction is not significant, right? So this is also something I will remove out. Okay, there is no bulk movement driven by pressure difference in this side. Then I also say that the V momentum equation, right? The V is the velocity in the y direction, right? So V equation can be neglected in the y direction. All these are neglected compared to the significant movement in a particular direction. Okay, so you have dou square v by dou y square also equal to 0. I can neglect it. Now, important thing is this condition here, which is dou p by dou y. Okay. So now let me just give you a background. So pressure, stagnation pressure at some point, so I'll call it 2, 0, 0 being stagnation, 2 being an allocation, right, is equal to static plus dynamic, okay, plus hydrostatic, correct? G, Z, and I'll call this 2, okay? Now, P01, in the initial condition, it's P1 plus half ρ1 square plus ρ1 GC. Now, there is no movement or flow due to dynamic pressure contributions are not there. So, I'm going to remove this particular component here, right? So then if I am going to calculate the difference in pressure, right? So then what is going to be happening? this minus this is equal to static. So let me write that. P2 minus P1 plus rho 2 GZ, correct? Minus, am I doing it correctly? Yeah. GZ equal to 0. Okay, so now what I'm saying is the difference in the static pressure, typically I'm just equating the two, and I'm saying that the difference in the pressure is equal to rho 2 minus rho 1 GZ, correct? Of course, the difference in the height comes into play. Delta Z, that's what we call. Okay. So now when you have rho 2 minus rho 1, right? So that means in our case, this will be equal to, can I take this in terms of rho infinity? Meaning there is a temperature at the infinity, so I can take rho infinity, correct? Minus the rho at the temperature, okay? So what I'm trying to do in this equation is I'm trying to say that the pressure gradient, the way I am writing it, right? I have a source term which is creating, and I need that source term separately so that I can say density varies only with the source term. That's the way of writing the Boussinesq approximation. So I say this pressure, totally the delta P is driven by this, correct? So I have a delta P term and a source term already. So I'm going to say that this is equal to rho infinity G. Okay? So then I call this as rho infinity G. So that together it denotes the pressure difference caused by the density change. Okay? So now this Boussinesq approximation then comes up to, if you see the y momentum equation, the dp by dy becomes this, and you have the source term. Okay, so you have a rho infinity minus rho times of g. Okay, so this is your Boussinesq approximation. Okay, now I want to kind of rewrite this in terms of temperature. I need an expression for temperature to actually directly couple it, right? So I call something called the beta or thermal expansion coefficient. All of you are aware of that. And I have the specific volume. So I'm calling this as rho, right? And this is 1 by rho. When you come there and write it at infinity, okay? So that means at the infinity conditions, free stream conditions. That's what the definition is. So then when I rewrite that, then this is what I will get. From here on, I can just simplify it to this. Okay. So essentially, what am I getting? I'm saying dou rho by dou T is equal to minus thermal expansion coefficient times rho infinity. This looks familiar. So I can say that delta rho, that is you see here, is equal to minus beta infinity rho infinity. This difference in temperature is what I have opened it out here. So I can essentially write my rho infinity times rho in terms of T. Okay. So your equation comes down to this. Everyone's clear till this point? I hope, because this is standard third year heat transfer, but I'm highlighting specifics which is important from the open form perspective. So what are the things we are doing? We are saying that, first of all, I am going to want to make my computation simple. So that means I need to not have density variation everywhere. I'm going to limit it to only a source term driven density, right? So I put a source term as rho g, correct? Denoting the difference caused by the density and the gravity effects, right? Now, this is not the full effect, correct? When you write the equation, when I'm writing it as rho g, there is actually a pressure term also involved. Actual difference is pressure difference caused flow. Flow is happening only due to the delta rho into g. So this is only one part of the rho. So we are bringing in this dou p by dou y as a p infinity which is the actual ambient density, and that difference together clubbed is called the Boussinesq approximation. And that we are now writing in terms of temperature using the thermal expansion coefficient definition. Okay. All right. So now I'm going to non-dimensionalize it because this is a very dimensional system. So if I change plate to plate, I will have different sizes. So when I non-dimensionalize it, I'm non-dimensionalizing u velocity in terms of a characteristic velocity, distances in terms of height of the plate, and temperature in terms of Tw minus T infinity. That is difference between your wall temperature and the ambient temperature. So when you have both of this, what happens is when you substitute, forget the red part of it, right? So you'll have the white equation. So to this, I am substituting the non-dimensionality and you will get this white type or white color part of the equation. So now to this, I am just multiplying to do some mathematical rearrangement. I'm multiplying both sides by h by vc square, which is your height by your square of the characteristic velocity. Okay. So when I do that and I focus on only this term, right? After I do that, I now say that I'm going to multiply. So for this vc square here, correct? And this g. So these two terms are already in this part. Okay. Now instead of h, I'm writing h cube by h square. Okay. If you cancel it out, it will be h, right? And then I am multiplying and dividing by gamma square. Okay. So then what happens is you can rewrite this as the Grashof number times 1 by Reynolds number square, which is Reynolds number. Let me change the color. So Reynolds number will be, if I compare Vc square, h square, and this square, this will be Reynolds number. And the remaining part will be Grashof number. Okay. So what does this mean? Product of Grashof number 1 by Re square. So what are we saying? This system of equations, when you apply the Boussinesq approximation, gives rise to two non-dimensional numbers. One is the Reynolds number, which is convection driven. Okay, it's inertia forces, right? Inertia versus viscous. And one is the Grashof number, which is the temperature difference versus the flow. Okay, so viscous force, right? So then you have a competition between two. One is forced convection and other is the natural convection. So if your Grashof by Re square, that product, right, is less than 1, then this is a forced convection system. If it is much, much greater than 1, then it's a natural convection system. Otherwise, it's a mixed convection system. Okay? So now what we're trying to say, in a vertical plate, okay, I will apply a particular delta T, okay? And when that delta T is being applied, you will have a flow that is being set up. And that flow will actually control your velocity distribution. That is important. Okay. So I'm going to now go ahead and talk about the boundary conditions straight away. I was thinking I will let you do the problem and then we talk, but then I think let's do it now. Okay. Okay. So in open form, now the boundary conditions are going to become tricky, right? Why is this going to be tricky, right? So if you have flow through a pipe, okay, what would you do? You would know the velocity at the inlet, okay? You will specify the pressure at the outlet, maybe 0 gauge pressure, and then you calculate the pressure at the inlet. So pressure is calculated. Now, why is this a simple, good boundary condition? Go back to your Navier-Stokes equation of solving. So you have the momentum equation, which is the temporal term plus convective term is equal to, there's a pressure gradient term plus diffusive flux plus source term, right? Okay. So when you specify a velocity of the inlet, so there is the mesh. So you're going to calculate solving each mesh and going forward, correct? So there is a clear velocity boundary condition at your inlet which will set up the flow. You know the velocity there. So when you know the velocity there and the back pressure that is at the outlet is known, the delta P gradient, because you'll be solving by the simple algorithm, there's a pressure equation, correct? So what will happen is you have set up an initial velocity, you can get a guessed velocity, and that will be plugged in so that you will get a pressure to satisfy this overall gradient of outlet pressure minus inlet pressure. So there's some flexibility there, correct? You're not over constraining the system. Okay. Now, what if I don't know the velocity at the inlet, right? Then what happens is I will have to have, say I know the pressure. For now, I know the pressure. So then there is a P1. Okay. So let me get into the iteration now. I have no clue what the velocity is, correct? So when I have no clue what the velocity is, I'm going to assume a velocity. So your u prime is there. But when I go into my continuity equation, I have P is fixed in every side. So the numerical stability cannot be there because my initial u is going to be significantly wrong. So typically this kind of equation is going to crash. Okay. So ideally you would need a velocity to kind of push through, but the pressure at the inlet boundary is not fixed so that it can iterate based on the outlet pressure. That's what that flexibility you want. Now, let us think of a condition where still we're trying to do the simulation in another class there. So there is an outlet flux. I know an exhaust fan is pulling out velocity. So I know the velocity at the outlet for sure, right? And in none of these cases, I'm talking to you about temperature, right? I'm only talking to you about velocities. So if you have velocity being pulled out, then in the problem when it starts, you have no clue what the velocity at the inlet is going to be. Okay. You have no clue. Depending, I have not told you the shape, whether it's uniform velocity everywhere. I don't know what the velocity is going to be. Okay. So then I will have to say that fine, let me give you a pressure, ideally, right? But then I've already kind of provided the pressure, the velocity outside, right? So if I give a pressure value here, it's not going to be too stable. Okay, so how do I know? I don't know the pressure very strongly also, correct? Because the velocity is also, I don't know the velocity, so it will not be able to correlate the velocity versus the pressure. So what people do in these conditions is they go to the stagnation pressure. So the stagnation is static plus dynamic pressure, correct? So if I at the inlet specify stagnation pressure, okay, then what it will do is it will say that, okay, my P is equal to P naught minus half rho U square. Okay, so then what it will do is it will plug in when it's solving. First, it will go and calculate P naught U, correct, basis an initial condition that you will set in the entire domain, and it will calculate pressure P and solve. Okay. So now what you're trying to say here is, you're trying to say that with the stagnation pressure, I am giving a little bit room of flexibility of iterative solving. Rather than fixing a pressure, static pressure, you get that pressure to be calculated by a guessed U. So there is a little bit more flexibility. So in this case, what is the boundary condition that's typically given at the inlet, right? Here at the inlet, you will be giving something called total pressure, which is equivalent to this stagnation pressure value. Okay. So total pressure is used. And then for velocity, you will give it as pressure inlet outlet velocity. Meaning you're saying that velocity get corrected with your pressure value once the pressure value is known. That's what you're trying to tell. Okay. So this is for only a flow condition. Correct. Now, if I have temperature driven, now coming to natural convection, Now I have a system which is heated. So this is my domain, right? This is like dotted lines. This is atmosphere. So this is my domain. So then I have no clue what this is going to be and this is going to be, correct? But I do know that this is going to be driven by hydrostatic difference, right? Rho GH. So I use something called PRGH total pressure. Okay. There's a version of PRGH pressure also, I think. Nothing, there's no big difference. So what you're essentially saying is P naught is equal to P minus half rho U square minus rho G delta H, where H is your current height minus H reference. Okay. So you're adding this hydrostatic component. Now, where do you remember this hydrostatic component? It had gone in the equation for the Boussinesq, right? So this is helping you set up that rho GH value for the y direction. Okay, so that is why you're giving this. And you would use something called the inlet outlet velocity, so that what will happen is, basis the pressure, the velocity will adjust itself. Okay. Now, what is the values of pressure you will give here? Okay. So because as you're moving up, there might be some influx also, right? So here you will give something called a fixed flux pressure, because this will be useful for, if there is some velocity, then basis your velocity, right? There'll be a velocity that if your code is calculating some u value here, then your pressure will get adjusted according to this velocity flux. It's not as strong as a dp by dx is equal to 0, not a zero gradient, right? You're going to adjust the gradient according to a u that is going to come in. So these are very flexible boundary conditions where you don't know what's happening, what is coming in and what is going out into your domain. It also helps in numerical stability. So these are the terms that you pretty much will see in the boundary conditions that are being used in today's tutorial of the vertical plate. And that will help you understand the background of why it is there. Okay. So with this, I will stop. So any questions at this point?
One question regarding this fixed flux pressure, how does it calculate the pressure given the velocity? Based on what equation?
So locally, what it will do is, so how will you calculate the flux? So in a boundary condition, so let me do a mesh. Okay. Let me put the question to you. So I am solving a bunch of equations here. And if I said dou p by dou x, this being the x direction, equal to 0, what will happen? How do you think this is going to be handled? So if I have, so let me zoom into my boundary cell. Okay. So this is the cell, this is the edge. And I say here it says dou p by dou x is equal to 0. Correct? So what will it do? Whatever pressure it calculates here, it is going to assign it to here. Am I correct?
Yes.
Okay. So now if I say fixed flux pressure, then I'm saying whatever pressure is going to cause my flow. So momentum, right? mv. What is the flux that is coming in here? It will solve iteratively here in this cell, so that my velocity, if u is going out here, my pressure difference will map to u. Okay, so my pressure delta p will have to map this u value that you see here. That will, what it will do is, it will internally, it's not a fixed condition. What it will do is, this u prime, it will substitute in this expression, it will say calculate the flux, and is all the mass flux equal to the pressure difference, it will solve, like the continuity equation will accordingly get fixed. Am I making myself clear? It's not like a single expression. It's the continuity equation that you will have to solve. So if you are getting a u value here, right? Let me rephrase. If you're getting a flux here, an m dot value here, basis your previous iteration of, there is a continuity equation, and then there is the momentum equation, where it is going to give you Now this is going to be in terms of pressure, rewritten in terms of pressure. Okay, so when you're having the momentum equation and you get a U star value, with the intermediate U star value, you will calculate the mass fluxes in every part of the cell. So when you calculate the mass fluxes in every part of the cell, you will re-put it here. There will be, when you write it in terms of P, there will be some mass flux terms on the RHS. It will not be 0. So when you put those mass fluxes here, what you are trying to say is the P is equal to those mass fluxes. Okay. At that point, it will not impose dou P by dou X is equal to 0. It will allow this equation to solve and calculate a pressure for this value here. You get what I'm saying?
Yes, got it.
Yeah. Anything else? Any other questions? Good question. So how will you check the CFL number in natural convection to fix the time step? So typically, natural convection is a trial and error process because you don't know your velocity. Am I correct? So what you will have to do is you will have to run 1 or 2 rounds of simulations with a particular delta t value. Okay. And understand the kind of velocity fields you are seeing. Okay. And then you calculate a CFL number roughly, because it's going to be basis your grid size, purely basis your grid size. So then you estimate a CFL number which is coming basis the velocity field. Okay. You will know. And then you have to make your mesh lesser so that your CFL number will fall under. So 2 controls are there. Either you make your mesh lesser or your time step lesser. You can only go a little bit lower for you can't go 10 power minus t is equal to 10 power minus 10. That may make sense. So at that time you'll have to adjust. So it's going to be a trial and error process. You can't off the round estimate your U. Any other questions?
Hello, ma'am.
Yeah.
Is there any possibility that if we are doing simulation for natural convection in 2D domain for PCM, patient material, and 3D domain for the same geometry, is there any possibility that we get the different phenomena of natural convection for 2D and 3D for
Absolutely.
liquid fraction?
Absolutely. Yeah. Your 2D, even for your forced convection, your 2D and 3D will be different. Okay. Now, for your 3D, for natural convection, you would see a different pattern. Okay. But if you're asking me if your flow, so for example, let me do this. Okay. So this is a 2D approximation of a plate, and you are getting some profile like this, right? Now, if I were to simulate a 3D domain of the same plate, I will definitely see differences in the thickness and the temperature range. Okay, but it will not be exorbitantly different, but it will be different by some factor. The trend will be caught, but values will be different. Okay, so you will not have something like exorbitantly different thickness. That will not be there, but it will be changing by a factor, definitely.
Thank you.
Okay.
Ma'am, are there any turbulence model with going along with this natural convection? Like, how do you select if we have to select?
Turbulence, right? So, see, typically that again is a very, it's a huge topic. It's only trial and error. So what you'll have to estimate, okay. So for turbulence models, if you're going to be using the standard K epsilon models, right? You are already in your mixed RE regions, okay? So you need to know your K and epsilon. For example, if you're solving your K and epsilon model, K epsilon turbulence model. So you will have to estimate for that, first of all, your inlet turbulent boundary conditions, right? So then where is your turbulence coming from? And from the inlet is the presumption. But in this case, so okay, so let me stop by and say what I have to say here in first a non-natural convection case. So if you have a pipe flow, right? And if you're done turbulence in the pipe flow, the turbulence is injected from the inlet, correct? So here you have a K and epsilon model, correct? Because you will have to inject the K and epsilon turbulent boundary conditions. Okay. Here, turbulence is injected at the inlet. Okay, so you will have to say my K is governed by I, epsilon is governed by some C, mu, L factors and all that. So you'll have to calculate I and L. Okay, length scale is the length scale of your domain. So here you're going to inject and give a turbulent boundary condition at the inlet. Now, as far as natural convection is concerned, you will have to use something called transition turbulence models. They are more accurate. What does it say? It says that now if you see your domain, your flow is not turbulent and injecting turbulence from the beginning. It will become probably turbulent after a little while, depending on the force. So here you will have a place where it will monitor your Reynolds number and see if your velocity is moving into the turbulence regime and then give a transition turbulence model. So you'll have to start using only transitional turbulence models. I think you have 1 or 2 transition turbulence models in OpenFOAM. So you'll have to use that than a pure K epsilon equation. Okay. Now, in these models, you might have to still specify some inlet kinetic energy, right? But when you calculate with the K and I formula, it will be very low, and that is fine, because these models will be built not to take turbulence from here, but to view the RE and then click on the turbulence model. Am I clear?
Yes, ma'am.
Okay. Okay, so there's someone saying for different geometries, how will someone know critical Rayleigh number so that I can decide which model can be used to reduce the computational cost? Okay. So I think this is again a very trial and error process, because for each geometry it is going to be different. So it's just trying to understand where is your, what is your A Grashof number that is coming out to be, your Reynolds number coming out to be. The other thing to monitor, if you're looking at really pure CFD question like this is, I would say that I would I will solve it as turbulence. And I would kind of monitor the K and epsilon value to see if it is also having turbulence. And the critical Rayleigh number, meaning is it purely natural convection? Is there... So that also I will monitor by looking at the temperature profiles. If you have a very strong U prime, V prime values, then it is going to be a little bit turbulence driven. And it will have, you'll have to see where that swap is happening to calculate what is your critical Rayleigh number. So that is only purely trial and error. That's how you can decide. And then subsequent decisions can be made basis what value it is to reduce the computation cost. Any other questions, doubts? So if there are no further questions, I think, John, you can go ahead with your vertical plate simulations. Okay.